Most pilots believe wake turbulence is only a problem near the runway, during takeoff and landing. But the truth is more unsettling. It's generated from the moment the nose lifts off until touchdown, as the FAA states. And those invisible spirals can persist for minutes, endangering aircraft at any phase of flight. So why does this happen? Every wing that generates lift also creates a rolling vortex off each tip, a spiraling tube of air that can reach tangential velocities over 150 knots behind a heavy jet like the Boeing 747. The heavier the aircraft, the stronger the vortex. And in calm air, these vortices can linger for up to 3 minutes. The FAA's own advisory circular puts it plainly. Wake turbulence is generated from the moment the nose of an aircraft lifts off during takeoff until the nose wheel touches down during landing. That means every flight, every phase, the danger is there, invisible, silent, and waiting. So how does an invisible force strong enough to flip a jet come into being? The answer lies in the simple act of flight itself. As a wing generates lift, high-pressure air from below spirals around the wingtip to meet low-pressure air above, creating a rolling cylinder of air called a wingtip vortex, T. And that's not all. These vortices trail behind the aircraft like invisible tornadoes, each one spinning in opposite directions. The strength of this wake is no accident. It is directly proportional to the aircraft's weight and inversely proportional to its wingspan. Heavier, slower, and smaller winged jets produce the most dangerous vortices. The FAA states it plainly. Wake turbulence is generated from the moment the nose of an aircraft lifts off during takeoff until the nose wheel touches down during landing. That means these vortices are present throughout the entire flight, not just near the runway, and in calm air, they can persist for up to 3 minutes, plenty of time to endanger a following aircraft. So what does that mean for the aircraft that follow? A Boeing 747, for example, can generate vortices with tangential velocities exceeding 150 knots, enough to roll a smaller plane completely upside down. That is why air traffic control mandates separation, 4 to 6 nautical miles behind heavy jets, and 6 behind super heavy aircraft, like the Airbus A380. So just how dangerous is the wake of a heavy jet? The numbers are sobering. A Boeing 747, at maximum takeoff weight, can generate wingtip vortices with tangential velocities exceeding 150 knots. That is powerful enough to roll a following aircraft completely inverted. Vortex strength is governed by a simple equation. It is proportional to aircraft weight and inversely proportional to wingspan. A heavy, short-span jet like a 747 produces far stronger vortices than a lighter, long-span one. This is why super heavy jets like the A380 require 6 nautical miles of separation behind them. And these vortices do not vanish quickly. In calm air, they can persist for up to 3 minutes, drifting downward and outward. A following aircraft that enters that zone may encounter sudden, violent rolling moments that exceed its control authority. That is why regulators mandate separation minima, or behind a heavy jet, large aircraft must wait 4 miles, small aircraft 5, and behind a super heavy like the A380, all following aircraft must stay 6 miles back. These rules are the only barrier between a routine flight and a wake-induced upset. So why did nobody stop it? The rules were clear, the physics understood. Yet on a clear December morning in 1995, a Learjet 35 approaching Santa Ana was about to discover that even a routine approach could turn deadly in seconds. The Learjet was following a Boeing 727 at a distance of just 3.7 nautical miles, inside the required separation. The NTSB later concluded that the Learjet entered a rapid roll to the right and descended uncontrollably, consistent with an encounter with wake turbulence. But here's the twist. This wasn't a takeoff or landing in the traditional sense. The Learjet was already on final approach, at an altitude where recovery was impossible. The pilots never saw the invisible tornado that flipped their aircraft. The Learjet's encounter proved that wake turbulence can be lethal even in clear skies on a routine approach. The NTSB's final report noted that the separation was inadequate, a stark reminder that the invisible force is always present, waiting for a moment of complacency. What happens when a pilot must abort a landing and go around? The separation rules assume a straight, predictable path, but a go-around changes the geometry entirely. The aircraft climbs through the wake of the preceding aircraft, and the invisible trap can snap shut. The International Civil Aviation Organization warns precisely of this. In the go-around, the aircraft may inadvertently fly into the wake of the preceding aircraft if not properly managed. The solution seems simple: climb above the preceding jet's flight path, but in the heat of the moment, that's easier said than done. And that's exactly what nearly happened in San Francisco in 2017. An Air Canada Airbus A320, cleared to land, lined up not on the runway, but on a parallel taxiway where 4 passenger jets sat waiting. The crew, distracted and fatigued, had misread the approach, and wake turbulence from a preceding 787 was cited as a compounding factor. To prevent such encounters, the FAA and ICAO have built a system of weight categories and separation minima. Heavy jets, those over 136,000 kilograms, must give way to lighter aircraft by at least 4 miles. Super heavy jets like the A380 require 6. But these rules only work if they are followed to the letter, and if the invisible vortices decay as expected. The rules exist, but they are only as strong as the awareness behind them. Every go-around, every approach, every moment behind a heavy transport demands respect for the invisible force that lingers in the air. Because when the separation breaks down, the consequences are measured not in miles but in lives.
But here's the catch. These vortices do not last forever. Their decay depends on the atmosphere itself. A crosswind can push a vortex off the runway centerline, while atmospheric turbulence, even light chop, can break it apart in seconds. The invisible tornado is fragile.
Which means pilots have a fighting chance, if they know what to look for. The FAA advises staying above the preceding aircraft's flight path during takeoff and landing, and to expect vortices to sink and drift downwind. A simple shift of a few hundred feet can mean the difference between a safe landing and a rollover. And yet, even with these procedures, the invisible force still claims victims. In 2019, a Cessna 172 crashed after encountering wake from a Boeing 737 at an uncontrolled airport. A stark reminder that awareness must be constant. The physics never take a break. But to truly understand the danger, we need to look at the vortex itself. A wingtip vortex is a tube of rotating air, typically 20 to 30 feet in diameter, that trails behind the wingtip. The core is nearly a vacuum, and the rotation can be so intense that it can flip a light aircraft. The strength of a vortex is given by a simple equation. It is proportional to the aircraft's weight divided by its wingspan. A heavy, short-span jet like a 747 produces far stronger vortices than a lighter, long-span one. This is why super heavy jets require more separation. Vortices decay through several mechanisms. Atmospheric turbulence breaks them apart, crosswinds push them away, and ground effect causes them to drift apart. When the air is calm, they can last 3 minutes. In turbulent air, they may dissipate in seconds. A crosswind can cause a vortex to drift laterally, potentially moving it onto the runway centerline. This is why pilots are advised to expect vortices to sink and drift downwind. A simple shift of a few hundred feet can mean the difference between safety and disaster. The go-around maneuver is particularly dangerous because the aircraft climbs through the wake of the preceding aircraft. The International Civil Aviation Organization warns that during a go-around, the aircraft may inadvertently fly into the wake, if not properly managed. So what can pilots do? The FAA advises staying above the preceding aircraft's flight path during takeoff and landing, and to expect vortices to sink and drift downwind. Awareness of wind conditions and separation is key to avoiding the invisible trap. So the lesson is clear: wake turbulence is not a mystery. It is a predictable force, governed by physics and shaped by the air. Respect the invisible tornado. Know when it forms, know how it decays, and always give heavy jets the space they demand. The sky is vast. Use it wisely.